Hello everyone. In this solution video, I'm going to do the stacked blocks problem. In this problem, we have two blocks, M1 and M2, being pushed across some ice. So there's no friction on this surface, but there is some friction between the two blocks, and we know the mass of the two blocks. And I want to know how hard can I push before M1 slides off of M2 slides off of M1. So I'm sure you've tried to do this before. If you have a slippery surface here and you push this block, you should expect this block to fall off. Well, the question in this problem is, how hard can I push before that actually happens? So this problem includes friction between these two blocks, but it's mostly a coupled motion problem where M1 is being pushed, M2 is only moving because M1 is acting on it and pulling it to the side. So to start this, the first thing we want to do, as with any Newton's second law problem, is draw a good free body diagram. There may be some reason to consider the whole system as one and do just one free body diagram for the whole thing, but I'm going to start by having two free body diagrams, one for M1 and one for M2. At some stage in the problem, you have to do that. So I'm just going to start from the very beginning by giving two separate free body diagrams. All right, so here's the beginning of my two free body diagrams. I've done all the forces that I think are totally obvious. I have a gravitational force downwards on the first block. I have a normal force upwards from the floor on the first block. And I have a force here pushing the first block to the right. For the second block, I have a gravitational force pulling downwards, and I have a normal force pushing upwards. But look how I've notated that as the same. That's obviously not the same normal force. This is from the floor. This is actually from the first block. So I'm going to write this as onto from 1. But as soon as I write this force, Fn21, I know that because these blocks are coupled, there has to be a Newton's third law pair of that force acting downwards equal to F1, 2. Those are equal in magnitude, opposite in direction. Okay, so now I want to make sure that these blocks are moving in an appropriate way. The bottom block is moving to the right. That's how I expect it to be moving. But the top block appears to have no acceleration. That's not right. If the bottom block is accelerating to the right, I want the blocks to be stuck together. The top block should also be accelerating to the right. There clearly has to be a force right there. So what is that force? Well, it's due to M1 acting on M2, but the only way a surface can act on another object is in the normal direction or through friction in the horizontal direction. So in this case, this must be a force of friction. It must be a force of static friction because the blocks are not moving relative to each other. And I'm also going to write that this is 1 acting on block 2. But now as soon as I write that, I know again from Newton's third law that there must be an equal and opposite force on the other block. So it's in the opposite direction. I'm going to label Fs 1, 2. So although there is no friction on the surface here, because the blocks are on top of each other, there is a frictional force right here, which is pushing back on the bottom block. So that might be a little bit of a strange concept, but it has to be there because of Newton's third law. We can't ever get away from Newton's third law. So from my perspective, I believe that these two free body diagrams are what we should be able to use to solve this problem. So the next thing to do is to write down Newton's second law in the x and y direction. I have two objects. Each object has an x and y Newton's second law, so I'm going to have 4 equations here. So in the x direction, I have just the force of friction pulling the block to the side. That is accelerating, so that means it is equal to its mass, m2, times its acceleration, a2. In the y direction, I have the normal force pushing upwards, gravitational force downwards. That thing is static in the y direction, so that thing is equal to 0. The sum of the forces in the x direction on the bottom block is the pushing force minus the force of static friction from the top block. That thing is accelerating, so the sum of the forces is going to be equal to its mass times its acceleration. And finally, in the y direction on the first block, we have the normal force pushing up, the normal force from the top block pushing down, and the gravitational force pulling down. There is no acceleration in the y direction, and so this thing is equal to 0. So at this stage, we sort of have a whole mess of equations, 4 separate equations. In principle, we could be solving for 4 unknowns, but all we really want to know is how big this force is if this condition is still satisfied. So there might be a number of things we could try, but the first thing I would say is we have 2 accelerations here, but these are coupled objects. These are objects which are connected together. And so those accelerations are not independent of each other, they're actually related. How are they related? Well, very simply, right? Because if m1 is moving with some acceleration, m2 must also be moving with the exact same acceleration or they would not be stuck together anymore. So actually we know that a1 is equal to a2. So we can rewrite that top equation as the frictional force being equal to m2 times a1. Okay, well that's cool because now we have this and this being the same, and this is the thing that we actually want to solve for. So let's try to solve for this a and plug it into that a right there. So that's a1 in terms of the frictional force in m2. And this is the expression that I get if I plug that acceleration right into there. Okay, so this is a good sign because right now I have this symbol and this symbol, but those two are related by Newton's third law. In fact, they're equal to each other. So now be a little bit careful because in our book and in class, what I've been talking about is the equal and opposite nature of Newton's third law pairs. But when I say that, I'm talking about the vector of those forces, not their magnitudes. Like that. So as vectors, they're opposite in direction, but these are now magnitudes, so they are exactly the same. So I'm going to simplify this down so that I just have F in terms of masses and the frictional force, which is that, and I'm just going to simplify that a little bit further, like that. Okay, now recall that the main thing we know about the frictional force is that it's equal to mu times Fn times the normal force. So I can put that in here, but recall that the static friction force is not an equality, it's an inequality mu s times Fn. So I'm going to actually end up with an inequality here, which looks like that. So the force that I'm pushing with has to be less than or equal to m1 over m2 plus 1 times mu s, which I know, times the normal force. How do I find the normal force? I can get it from right here. Because the normal force minus the gravitational force is 0, the normal force is equal to the gravitational force. The normal force is m2 times g in this case. Like that. I'm going to make one final simplification, and that is that I have an m2 on the bottom here, so if I just take this m2 and multiply through, I'll get an m2 right here, and that one will cancel, and that will give me a little bit of a cleaner result. And that is that the maximum I can push with is m1 plus m2 times mu s times g, and that is 529.7 newtons. So let's reflect on the process that we use, because this is very common for these problems that have more than one body in them. So we started with the free body diagram, one for each body, and what we did is we checked to see that our free body diagrams made sense, both with the acceleration and with the presence of the forces. So we knew this force had to exist, but because we knew that there must have been a force here opposing the motion on this block. So we have to be very careful to make sure we check the acceleration is right. Also check that Newton's third law is verified. After doing that, we wrote down all of Newton's second law. In that case, there were 4 separate equations. And then comes the kind of tricky task of figuring out what equations are going to be helpful. But at some point, you're definitely going to have to use the fact that the two accelerations are the same because the two boxes are coupled together. That's a condition of the problem, that they have to be coupled. That means you should expect to see that as part of the solution. But once we got that, it was pretty easy to chase down what the answer was. Okay, great. That's the solution to this problem. I hope it has been helpful, and I will see you guys next time in class.